Okay, so acids and bases and pH. So think about water. All right, just pure water. Water molecules are hydrogen bonded to other water molecules. Okay. Now, occasionally, some of the water molecules disassociate, which means that one water molecule literally breaks apart into a hydrogen, leaving a hydroxyl group. Now, because there's lots of other water molecules around, that hydrogen, which is basically a proton, or we can call it a hydrogen ion, it will, I guess, stick to, or it will be attracted to another water molecule, to the oxygen side of another water molecule, because the negative charge on the oxygen on the water molecule. Okay? So,
to the other oxygen?
sorry?
You said when it transfers over, it's only to the other oxygen molecule?
It will kind of, look at the diagram on the board, see we've got our good old H2O. When there's a spare hydrogen ion floating around, because this is the negative side to the molecule, it's going to be attracted to that side. Yep. And so now we've got this particle, which the water molecule is neutral, we're adding one positive charge. This is overall a positive charge, and we call that a hydronium ion. Okay? Now what's left when a water molecule breaks up, when the hydrogen breaks off, we've got a hydroxide ion. That. So they float around. That's sort of a fairly accurate picture of what happens. But these will rejoin quickly to form two water molecules again. Is everyone okay with that? So it's in a flux. That's why the arrows on this equation run in both directions. Okay? Now, we're going to kind of keep it simple. We're not going to worry about a hydronium ion. Okay? We're just going to think about water molecules and water molecules disassociating, which they do, and then coming back together. Disassociating, coming back together. Not all of them do it all the time by any means, and it's kind of a rare event that any water molecule is going to do it anyway. But in a glass of water, you've got millions upon millions of water molecules. Even a rare event is going to happen quite often with that number of molecules. Okay? So there's our water molecule. It can break apart and it can form a hydrogen ion, which is basically a proton, and a hydroxide ion. Is everyone okay with that? Yep. There's our hydrogen ion, there's our hydroxide ion, and everything balances in that equation. Even the charges balance nicely. Okay? Right, and that's in reverse. Like I say, some water molecules break, and then they quickly join again. All right. Now, when pure water, this happens in pure water, the ratio of hydrogen to hydroxide ions must be a 1-to-1. It must be equal. Because each water molecule gives rise to one of each. So the ratio of one to the other must be equal. Is everybody okay with that concept? Just the ratio being equal? Yep. So that means that the concentration of each of those particles must also be equal. The hydrogen ion concentration is equal to the hydroxide ion concentration in pure water at 25 degrees Celsius. Okay? All right. Is everybody comfortable with these square brackets? Whenever I put square brackets around something, it means concentration of. And concentration of, it's a measure of how many of these per unit volume. We usually talk about how many of these there are per litre of the liquid, for example. Okay? All right. So, there's a glass of water at any particular moment, a whole bunch of water molecules, not many, but a number of them in a glass of water, disassociate. We have equal concentrations of hydrogen and hydroxide ions, and then they come back together. And other ones will disassociate. Okay? And when we've got an equal ratio of these, then that solution is neutral in pH. It's neither an acid nor a base. And we can measure its pH. And does anybody know the pH for a neutral solution? 7. pH 7 on the scale. All right? And I'll elaborate on that in a moment. Okay. All right. So in an aqueous solution, and you know what an aqueous solution is, don't you?
Something in water.
It's one where water is the solvent. Yep. At 25 degrees Celsius, this relationship is always true. The concentration of hydrogen ions multiplied by the concentration of hydroxide ions is always 10 to the negative 14. It's just because of the properties of water, all right, at 25 degrees Celsius. That just happens to be the relationship and the numbers that we've got. Is everyone okay with that? It's just the properties of water. It's just the way water is. Nothing magical about it. So that relationship is always true. Now, in pure water at 25 degrees Celsius, the hydrogen ion concentration is 10 to the negative 7. Right? There's 1 times 10 to the negative 7 hydrogen ions per litre of water. That's just the way it is. Now, because that relationship is always true, if hydrogen ion concentration is 10 to the negative 7, what must the hydroxide ion concentration be? Good, 10 to the negative 7. And that must equal, and it does, 10 to the negative 14. All right, good. So if you know one, you can always figure out the concentration of the other. Yep? Okay. All right, there we go.
Oh, that's cool.
You like that?
Yeah.
All right. But other substances that we add to water can easily change the ratio of hydrogen to hydroxide ions, and it can easily change the concentration of one over the other. Other substances that we add. Okay? And many, many, many things that dissolve into water can change these numbers, can change the concentration and therefore the ratio. Okay? All right, so some substances that we add to water can increase the hydrogen ion concentration. You can get more hydrogen ions. And when we increase the hydrogen ion concentration, we also decrease the hydroxide ion concentration. Any substance that increases the hydrogen ion concentration is an acid. Okay? So substances that we can add to water sometimes increase the hydrogen ion concentration, and they're acids. Now remember, a hydrogen ion concentration greater than 10 to the negative 7 is going to be any exponent that is numerically smaller than 7. Is everyone okay with that? Yeah? So anything that's less than 10 to the negative 7, sorry, greater than 10 to the negative 7, 10 to the negative 6 would be a higher concentration of hydrogen ions. Okay? Good? Right. Now, conversely, some substances we add decrease the hydrogen ion concentration and increase the hydroxide ion concentration. And we call those substances bases. Any substance that does that is a base, and the hydrogen ion concentration will be less than 10 to the negative 7. Okay? What kind of substances do you think we can add to water? What kind of substances are we talking about? Are these common? Are these rare substances? Almost anything. Now, not everything changes this, but many substances do. For example, just the carbon dioxide in the atmosphere and from your breath change it. they actually increase the hydrogen ion concentration and decrease the hydroxide ion concentration, and they form a weak acid. All right? You can take a little beaker of distilled water or deionized water. I can blow into it with a straw, and I can put a pH probe, and I can measure the pH change, and it turns into quite an acid at about pH 4 or 4.5. Okay? All right. Some substances decrease this. Anybody think of a substance that can significantly decrease the hydrogen ion concentration? Bleach does. Oven cleaner does. Milk of magnesia does. Ammonia does. Yeah. All right. So, is everybody good with that concept? Some substances can increase this and some can decrease it. Some substances are acids, some substances are bases. Okay? All right. So, here's a good example. Hydrogen chloride, which is actually a gas and it's super soluble in water. If we add this to water, we can bubble it through water and it very readily dissolves, and when it does, it forms hydrogen ions and chloride ions. Well, you can just see by the substance we're adding hydrogen ions, right? It massively increases the hydrogen ion concentration. In fact, it increases it to about 10 to the negative 2. Many orders of magnitude, because we're adding tons of hydrogen ions. All right? So what's going to be our resulting hydroxide ion concentration? What's it going to be? Negative 12. The number that's missing is 12, but it's going to decrease it to negative 12. Okay? 10 to the negative 12 is much smaller than 10 to the negative 2. All right, good. Okay. All right, so far we've only talked about hydrogen ion and hydroxide ion concentrations. All right? We don't use hydrogen ion concentrations when we're talking about pH and the pH scale. All right? We actually convert it into something that's a little more straightforward, but the numbers you're going to be familiar with. So the pH of a solution is defined as, this is a bit of a tongue twister, the negative log of the hydrogen ion concentration. Now if you want, you can get your calculators out and you can tap these numbers in, but I'll show you anyway. So the pH is the negative log of the hydrogen ion concentration. So I can give you any hydrogen ion concentration, and I'll say take the negative log, that is the pH value of that solution. Okay, and it looks something like this. I'll take you through an example. If we get a neutral aqueous solution, like water at 25 degrees Celsius, where the hydrogen ion concentration is 10 to the negative 10, 10 to the negative 7, and I take the negative log of 10 to the negative 7, I get 7. Easy. Yep. What's the negative log of 10 to the negative 12? 12. Good? Nice. Makes it very straightforward. Okay? So I just want to show you where the pH numbers come from, what it actually is. I'm never going to ask you to take the negative log of the hydrogen ion concentration, but at least now you know where those numbers on the pH scale come from. All right? So the pH scale then is a measure of the hydrogen ion concentration, but on a log scale. When we have a pH of 7, that's a neutral solution. And when we've got a pH value which is smaller than 7, that gives us an acidic solution. And when we have a pH value that's greater than 7, we've got a basic solution. Now, the closer the number is on the pH scale to 1 or 0, the stronger the acid, and the closer the number to 14 on the pH scale, the stronger the base.
So closer to 0 is a stronger acid, closer to 14 is a base.
Yep. Yeah, mostly. All right. So, here's our beakers then. There's our basic solution. Can you see that we've got a lot more hydroxide ions than we do hydrogen ions? And our acidic solution, there's a greater proportion of hydrogen ions relative to hydroxide ions. Good? All right. So for our acidic solution, you don't have to tell me exactly what the pH is, because I couldn't tell you, but ballpark a pH for that acidic solution. Guess a pH value for that acidic solution.
9.
What do you absolutely positive know it's not going to be? What pH value will this not be for this acidic solution?
It will be less.
It's going to be less than 7. Give me a number. 5, 4, 3, 2. Okay. What about 7.2? Is that an acid? No. What is it? Base. It's just on the basic side of neutral, isn't it? So maybe this is a pH 3. What could this basic solution be? Give me a pH for it.
8.
Maybe 8.
9.
Maybe 10. Okay. Good. Okay, so here's a scale then. All right. And it will show us some of the common substances. And it shows you what their pHs are. We can very easily measure pH with a pH meter. We can use some indicator paper and have a colorimetric test. So pure water is at pH 7. Now, funnily enough, when we take our deionized water in the lab and we run it into a beaker, now we have the apparatus that we have to make our deionized water is actually very, very good. All right? There are minute amounts of substances left in there. But as soon as we run it into a beaker, the pH drops quickly to about pH 4.5. But it should be neutral, right? Because it's almost pure water. What do you think caused it to drop? It's the carbon dioxide dissolving into it. Yeah? And that forms the weak acid. It's literally a sponge for carbon dioxide. Okay? So if we could keep that carbon dioxide out, it'd be right around pH 7. All right, so let's have a look at some common substances. So urine and saliva, what are they? Acidic or basic? Slightly acidic, very slightly. Black coffee at pH 5, tomato juice and beer pH 4. Look at that, vinegar, wine and cola pH 3. It's quite acidic. Let's take gastric juice, lemon juice and pool acid. Muriatic acid it's sometimes called. Super, super strong acids, pH 2. Now that should explain why when you vomit, you get that nasty burning, don't you, in your esophagus and all around your throat. It's the acid. The linings are not equipped to keep that, to protect yourselves from that acid. So it's the most acidic environment in your body is your stomach. It's because your stomach produces hydrogen chloride, which forms hydrochloric acid. Okay? Now, when you take that little purple pill, you've all seen the ads for it, right?
Tums?
In fact, not Tums or Pepto-Bismol, but things like Zantac,
Oh.
right? Any of those things. Do you remember what they're called, what they actually do? Many of them. They're not antacids exactly. Some of the substances you take react with the acid and neutralize it, right? Milk of magnesia does that. Tums do that. They react with the acid. They're chalky, and they neutralize it that way. But what about those other ones? Pepsid AC, I think it's another drug. Do you remember what they say in the commercials?
No, because I don't know what product you're talking about.
You don't?
No.
Zantac? It's what you might be prescribed if you have acid reflux or an ulcer in your stomach.
Oh, I've never.
Those substances are called proton pump inhibitors. That's what many of them do. In your stomach, there's your bag, that's your stomach. There are cells which pump in protons, hydrogen ions, loads of them. It's what makes the environment really acidic. When you've got acid reflux, it's the acid making its way back out your stomach up into your esophagus. The lining of your esophagus isn't geared to protect yourself from the acid. Your stomach lining is.
So is that like, did you just have an increase in the pump, or is it a normal? Is it always going at a normal rate?
So sometimes the problem is, if you've got a medical condition, is that this is overactive. Sometimes your diet. Sometimes it's the little valve just there doesn't work properly and lets it out. Sometimes you simply eat too much and you sit down and this bag squeezes and the food exits back. If that valve has become compromised especially. All right? Don't eat too much. Don't get a big pot belly unless it's through beer drinking.
My fatty acids allow me to.
Maybe.
Yeah?
No. But so one way those drugs work is they turn off proton pumps. They turn off the pumps which move protons into your stomach. That's how they switch off acid production. Okay? Have a little look. Next time you're in Walgreens or CVS, go look. Zantac or one of those other and see what it does. They're called proton pump inhibitors, many of them. Okay. So now let's look on the basic side. So seawater and your small intestine. Just downstream of your stomach, you enter a basic environment. In fact, there's a little duct called your common bile duct, which releases substances into your duodenum, which is just downstream of your stomach, and those substances neutralize the acids and make the environment a little on the basic side, as is seawater, about pH 8. And then we've got things like milk of magnesia. Well, that's what you use if you've got an upset stomach. It basically reacts with the acid, gets rid of the acid conditions in your tummy. Household ammonia, bleach, and oven cleaner, extremely basic. Bleach is oven cleaner is an incredibly corrosive substance. All right? And it is NaOH. So when it dissolves in water, it gives you a sodium ion and a hydroxide ion. And all these hydroxide ions are what shift the equilibrium and give you that huge concentration of hydroxide ions. Good? All right. Okay, so most organisms overall are around or close to pH 7. Obviously in your body you've got environments that are widely differing in their pH. So you've got different compartments in your cells that are different pH, different compartments, different organs that house different pHs, but by and large you're pH 7. Okay? Now chemical reactions are extremely sensitive to the pH of the aqueous solution they occur in. Very, very sensitive. So if the pH is outside of an optimal range, the chemical reaction may not proceed at all. So, if you're too acidic or too basic, sometimes the reaction doesn't proceed, or it may not proceed smoothly. Chemical reactions are very sensitive to pH changes. One reason for that is you have proteins. Proteins are enormous molecules and they have very complex structures. If we change the pH, their structure can slightly change. They're very sensitive to the pH. And if their structure changes, so does their function. Okay? Now, sometimes that's a bad thing, but sometimes it's a very good thing. Sometimes what we can do is regulate chemical reactions by simply changing the pH. Your body's quite easily can change the pH. Add some hydrogen ions, take them away. If you change the pH to the optimal value, the reaction proceeds. If you change it to the suboptimal value, maybe the reaction switches off or ceases. Yep. Okay. All right. But we need usually to maintain the pH of an environment within very strict limits. Your blood is a good example of a tissue in your body whose pH range is kept within very, very narrow limits. You're right around pH 7.2, 7.4 in your blood without much deviation from it. If it deviates much more, you don't feel so good. So your body has to regulate the pH of certain environments, and it does that by using chemicals called buffers. So buffers are chemicals which regulate the pH, keeps the pH within very strict limits. Okay? And you have lots of chemical buffers in your blood. That's kind of handy, right? Because think about all the junk that you eat. What was Coca-Cola? pH what? 3. Good grief. Lemon juice? 2. I don't know how many of you glug battery acid, but, you know, you're eating things that are acidic, you're eating things that are very alkaline. Yep. Now, they don't all make it in your blood instantly, but there is some movement across into your blood, other chemical reactions in your blood, and buffers. Keep them within strict limits. If there's too many protons, they can mop them up, and if there's not enough, they can release them. Okay? All right. So they keep constant.
So they only release or suck up hydrogen?
Hydrogen ions, you know, no, I'm going to say some of them work with hydroxide ions.
Okay.
But I don't know enough about those buffers.
So you're not going to say yes or no, it's just kind of like, eh.
I'm going to say it's both.
Okay.
I'm going to say it's both. It's got to be both. All right. So that's it for pH. Any questions on pH? Feel comfortable? Okay. So there will be some questions on pH on your next exam, exam number 2. Okay. So exam number 2 will be pH and everything to the lecture period right before that exam. Yeah.
Are you wanting us to remember like things that are on the pH scale? Like as far as like items, like you said, like battery acid?
So that's a good question. No, I don't want you to remember everything on that scale. I do want you to remember things like stomach acid. Oh, yeah, your stomach's at pH 2. I do want you to remember your small intestine, the duodenum, just downstream of your stomach, is about pH 8. There are other pH values for different parts of your body that I'll give you that I do want you to remember. You know, do I care that you remember the pH of ammonia? Not really. But I do want you to understand that, yep, ammonia, bleach, and oven cleaner, sodium hydroxide or lye, they're all very basic. All right. And obviously formic acid is going to be a what? An acid, yeah. There you go.
What pH is it? How strong is it? Close to
Formic acid, I don't know.
I mean, it's something pretty strong.
I don't think I think it's right around pH 3 or 4. I don't know, but I'm going to guess 4. See if my memory's correct. I don't know.
That's still pretty strong.
All right, so here's the deal. I know I used the word strong acid and weak acid and correlated that with pH. There's some truth in that and maybe not some truth in that. If you go take chemistry classes, they'll go into lots of detail with that. All right? Okay. All right, so here's what I want you to start to really practice and think about. Your reading, writing, and note-taking skills. All right? When you read, don't read science like a novel. Yep. Read it, every word of every paragraph, and make sure you understand everything you're reading before you move on. A little tip. What's a little tip at the end of every paragraph? Right, maybe a 1-sentence summary of that paragraph, or maybe a 2-sentence summary. Yep, that will keep you on track and that will keep you from sort of zoning out. All right? Note-taking. So don't write down what's on the PowerPoints. Obviously, they're posted. Try to write the things that aren't on there, or meld the two. What I say, write on the board and what's on the PowerPoint, and construct something new rather than repeat something that's old. Okay.